NENOMATICA, where mathematics meets YouTube excellence. The seventh law of power. Welcome to this math tutorial. Today, we're going to determine whether the product of negative numbers is positive or negative. Let's examine this example. We need to determine whether the expression negative 1 to the power of negative 13 times negative 2 to the power of negative 12 times negative 3 to the power of negative 11, continuing all the way to negative 45 to the power of 31, is a positive or negative number. Before we solve this problem, let's review a key rule. When a negative number is raised to a power, the result depends on whether that power is even or odd. For a negative base with an even exponent, the result is positive. For a negative base with an odd exponent, the result is negative. Fade in, let's start solving our problem. We need to determine the sign of each factor, and then find the overall sign of the product. First, let's look at negative 1 raised to the power of negative 13. Since negative 13 is an odd number, and a negative base raised to an odd power gives a negative result, negative 1 to the power of negative 13 equals negative 1 over 1 to the power of 13. Since 1 to any power is still 1, this equals negative 1. Next, let's examine negative 2 to the power of negative 12. Since negative 12 is an even number, and a negative base raised to an even power gives a positive result, we get positive 1 over 2 to the power of 12. So negative 2 to the power of negative 12 equals 1 over 2 to the power of 12, which is positive. For the third term, negative 3 to the power of negative 11. Since negative 11 is an odd number, the result will be negative. So the sign of this term is negative. We can continue this pattern for all terms. Let's analyze what we have so far. When the exponent is negative and odd, the result is negative. When the exponent is negative and even, the result is positive. Let's count how many terms will be positive and how many will be negative. From 45 terms in our product, let's count how many have odd exponents and how many have even exponents. We have negative exponents from negative 13, negative 12, negative 11, all the way to positive 31. Looking at all 45 terms, we need to count how many have negative odd exponents or positive even exponents, which would give negative results. Now, to determine the sign of the entire product, we need to remember another rule. When multiplying numbers, an odd number of negative factors results in a negative product, while an even number of negative factors results in a positive product. Since we have 23 negative factors, which is an odd number, the entire product will be negative. Therefore, the result of our expression is a negative number. Let's look at our example. If a equals 3 to the power of 5 and b equals 2 to the power of 7, write the result of 27a cubed divided by 512b cubed, all over 9 to the 9th power times 4 to the power of negative 3 as a single power of a number. Let's start by substituting the values of a and b into our expression. We're given that a equals 3 to the 5th power and b equals 2 to the 7th power. First, we'll substitute these values into our expression. Next, we need to simplify the powers. We know that when we have a power raised to another power, we multiply the exponents. So 3 to the 5th power cubed becomes 3 to the 15th power. And similarly, 2 to the 7th power cubed becomes 2 to the 21st power. Now we'll express the numbers in terms of powers of their prime factors. 27 is 3 cubed. 512 is 2 to the 9th power. 9 is 3 squared. And 4 is 2 squared. Let's substitute these values back into our expression. Now, we need to simplify the numerator and denominator. In the numerator, we have 3 to the 18th power divided by 2 to the 30th power. In the denominator, we have 3 to the 18th power times 2 to the negative 6th power. First, let's simplify the fraction with the 3 terms. 3 to the 18th in the numerator divided by 3 to the 18th in the denominator equals 1. Now, let's combine the exponents in the denominator. When we multiply powers with the same base, we add the exponents. So 2 to the 30th times 2 to the negative 6th is equal to 2 to the power of 30 plus negative 6, which equals 2 to the 24th power. Finally, we need to write this as a single power of a number. We know that 1 over a to the power of n equals a to the power of negative n. So 1 over 2 to the 24th power equals 2 to the power of negative 24. And that's our final answer. 2 to the power of negative 24. Today we'll be proving several important exponent rules that are fundamental to algebraic manipulation. Let's start with our first property. Here we want to prove that a over b raised to the power of negative m equals b over a raised to the power of m. Let's begin by rewriting the expression on the left side. We know that a over b raised to negative m can be written as a over b raised to negative 1, and that whole expression raised to the power of m. Next, we can rewrite a over b raised to negative 1 as a to the power of negative 1 over b to the power of negative 1. We know that a to the power of negative 1 equals 1 over a, and b to the power of negative 1 equals 1 over b. So we get 1 over a divided by 1 over b, which is 1 over a times b. This simplifies to b over a. So now we have b over a to the power of m, which is exactly what we wanted to prove. Now, let's move on to our second property. We want to prove that a to the power of m divided by b to the power of n equals a to the power of m times b to the power of negative n. First, let's rewrite the division as a fraction. A to the m divided by b to the n becomes a to the m over b to the n. Using the definition of negative exponents, we can rewrite this as a to the m times b to the power of negative n, and that completes our proof of the second property. Finally, let's examine our third property. We want to prove that a to the power of negative n equals a to the power of negative 1, all raised to the power of n, which also equals a to the power of n, all raised to the power of negative 1. Let's start with the definition of a negative exponent. A to the negative n equals 1 over a to the n. Next, let's look at the second expression. A to the negative 1, all raised to the power of n. We know that a to the negative 1 equals 1 over a, so we have 1 over a all raised to the power of n. Using the power rule, this becomes 1 to the power of n over a to the power of n. Since 1 to any power equals 1, we get 1 over a to the n. Now for the third expression, a to the n all raised to the power of negative 1. Using the negative exponent rule, this equals 1 over a to the n raised to the power of 1, which simplifies to 1 over a to the n. Since all three expressions equal 1 over a to the n, we've proved that they're all equivalent to each other. Let's see a numerical example to verify this. If we take a equals 4 and n equals 2, we get 4 to the negative 2 equals 4 to the negative 1, all squared, which equals 4 squared, all raised to the negative 1 power. 4 to the negative 2 equals 1 over 16. 4 to the negative 1 equals 1 quarter, and 1 quarter squared is 1/16. 4 squared is 16, and 16 to the negative 1 is 1/16. So we can see that all three expressions equal 1/16, confirming our proof. To summarize, we've proven three important exponent properties. First, a over b raised to the negative m power equals b over a raised to the m power. Welcome to our lesson on comparing exponents. Today, we'll learn how to compare expressions with negative and fractional exponents. Let's start with our first example. We need to compare 3 to the power of negative 1 and 3 to the power of negative 2 and determine which one is greater. Let's first convert these expressions to fractions. 3 to the power of negative 1 equals 1 over 3, and 3 to the power of negative 2 equals 1 over 9. Now we can directly compare these fractions. 1/3 is greater than 1/9, so 3 to the power of negative 1 is greater than 3 to the power of negative 2. Let's move on to our second example. We need to compare 2 to the power of 0 and 2 to the power of negative 5. Remember that any number except 0 raised to the power of 0 equals 1. So 2 to the power of 0 equals 1. For 2 to the power of negative 5, we use the negative exponent rule again. This equals 1 over 2 to the 5th power, which equals 1 over 32. Now, we can directly compare 1 and 1 over 32. 1 is greater than 1 over 32, so 2 to the power of 0 is greater than 2 to the power of negative 5. Now, for our third example, we need to compare 0.5 to the power of negative 2 and 0.6 to the power of negative 2. Let's first convert 0.5 to a fraction. 0.5 equals 1/2. So 0.5 to the power of negative 2 equals 1/2 to the power of negative 2. Using the negative exponent rule, this equals 1 over 1/2 squared, which is 1 over 1/4, which equals 4. Similarly, let's convert 0.6 to a fraction. 0.6 equals 6/10, which we can simplify to 3/5. So 0.6 to the power of -2 equals 3/5 to the power of -2. Using the negative exponent rule, this equals 1 over 3/5 squared, which is 1 over 9/25, which equals 25 over 9, or 5/3 squared. Now, we need to compare 4 and 25 over 9. 4 equals 36 over 9, and 36 over 9 is greater than 25 over 9. Therefore, 0.5 to the power of -2 is greater than 0.6 to the power of -2. For our final example, we need to compare -5 to the power of -2 and -5 in parentheses to the power of -2. It's important to understand the difference between these expressions. In the first case, we have the negative of 5 to the power of -2, while in the second case, the entire -5 is raised to the power of -2. Let's calculate -5 to the power of -2. This equals -1 times 5 to the power of -2, which equals -1 over 25, or -1/25. Now for -5 in parentheses to the power of -2, this equals 1 over -5 squared, which equals 1 over 25, or 1/25. Now we need to compare -1/25 and 1/25. Since -1/25 is less than 1/25, -5 to the power of -2 is less than -5 in parentheses to the power of -2. Let's summarize what we've learned. When comparing expressions with negative exponents, it's helpful to convert them to fractions first. Remember that a to the power of -n equals 1 over a to the power of n. Also, any non-zero number raised to the power of 0 equals 1. When dealing with negative numbers, be careful about parentheses and order of operations. With these rules in mind, you can compare any expressions with negative or fractional exponents. Welcome to our mathematics lesson. Today we're going to learn about negative exponents and their properties. Let's look at our example. For positive real numbers a and b, we'll explore the relationship between a to the -b power and its equivalent form. Let's begin with a reminder about negative exponents. For positive real numbers a and b, we have that a to the -b power equals a to the -1 power raised to the b power. This equals the fraction 1 over a to the first power, all raised to the power of b. This can be rewritten as the fraction 1 over a to the first power, all raised to the power of b. And finally, since 1 raised to any power is still 1, and using the power of a power rule, we have a to the -b power equals 1 over a to the b power. Now let's examine a theorem. For any positive real number a and any rational number r, we have that a to the negative r power equals 1 over a to the r power. Let's prove this theorem. We'll start with the given information. R is a rational number and a is a positive real number. We need to prove that a to the negative r power equals 1 over a to the r power. Since r is a rational number, we can express it as a fraction p over n, where p and n are integers and n is not 0. Let's substitute this into our expression. A to the negative r power equals a to the -p over n power. Using the property from our reminder, this is equal to a to the -1 power, all raised to the p over n power. We know that a to the -1 power equals 1 over a, so we can substitute this in to get the fraction 1 over a, all raised to the p over n power. Next, we can rewrite this as 1 to the power of p over n divided by a to the power of p over n. Since 1 raised to any power equals 1, and noting that p over n equals r, we get 1 over a to the r power. Therefore, we have proven that a to the negative r power equals 1 over a to the r power for any positive real number a and any rational number r. This is an important property of negative exponents that helps us simplify many expressions. In summary, we've seen how to handle negative exponents. Remember that when we have a to the -b power, we can rewrite it as 1 over a to the b power. This property works for any positive real number a and any rational exponent r. These rules help us simplify complex expressions involving negative exponents. Let's end with a quick example. If we have 5 to the -2 power, we can rewrite this as 1 over 5 squared, which equals 1 over 25. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.